Alright, so for an LDR, it is a light-dependent resistor. Now, a light-dependent resistor is an electrical component where when light falls upon the material, the electrons are able to gain energy, and then those electrons are free to conduct electricity. So, because it is made of a semiconductor, there are two different types of bands. You've got a valence band and a conduction band. Now, you think of the valence band as not the outer shell, but the in between the inner shells and the outer shells. I mean, something called orbitals. And it is these electrons that orbit the nucleus into between the inner shells and the outer shells. And once you've given energy to those electrons that is in the valence band, so in between the inner shell and the outer shell, it will go into the conduction band, where these electrons are able to move around the substance, the material. So if you look at the top diagram here, the electrons, where it is the black circles, so the electrons are stuck in the sense that it doesn't have energy to escape from the nucleus. However, if you look at the bottom diagram, so as you keep on adding the temperature, or in this case, you for light-dependent resistor, as you increase the number of photons, because the photons is transferring energy to the electrons have enough energy, and they move from the valence band to the conduction band. And in the conduction band, the electrons are able to move freely within the metal. And similar to a thermistor, as you increase the temperature for the thermistor, the resistance will decrease. But for an LDR, as the light intensity increases, the resistance also decreases. Okay, so in general, what are LDRs? Now, the LDR stands for light-dependent resistor. They're electrical component that when light is shone upon the material, the resistance will change. And just like a thermistor, as the temperature increases, the resistance decreases. So for a light-dependent resistor, as the light intensity increases on the material, the resistance will decrease. So it is a semiconductor. When it is dark, when there are no photons acting on the material, the resistance is very high because you haven't released the electrons in the semiconductor. So therefore, because there is no current, because there is no electrons moving freely, the resistance is very high. And so as you gradually increase the number of photons, as you increase the light intensity, the electrons will be released. So the density of charge carriers, in this case the electrons, will increase. More current meaning less resistance. Where do you use LDRs? Now, an LDR is a light-dependent resistor. So where would you use an LDR? So for example, street lamps, sports venues, and smartphones, perhaps laptops, and even telescopes. Because when the light intensity increases, then the resistance will decrease. And when it's dark, the resistance is very high. Now, if a light source is further away from the detector, that would imply that the light intensity will decrease because there's less chance of the photons hitting the detector. The closer you are, the closer the light source is to the screen or detector, the more light intensity falls on the detector. So how would you do an experiment where you vary the light intensity? So you would vary the distance between the detector and the light source, because the further away the light source is away from the detector or the screen, the less light intensity. Now, you need to perhaps do it in a darkened room, or you need to shield the light away from other background light. So you could use a darkened box, a darkened room, or maybe a dark roll, so a kitchen roll, where you just direct the light to the detector. Okay, so if the light source is further away from the LDR, the light intensity is much less. As the distance from the LDR increases, the light source is further away, the resistance will increase. So if the distance from the LDR decreases, then the resistance will decrease. Alright, so let's go through some definitions. Now the definition for voltage is energy per charge. So 1 volt would be for every coulomb you would apply 1 joule of energy. And the charge for 1 electron is 1.6 times 10 to the minus 19 coulombs. So that means for 1 coulomb, you have 6.25 times 10 to the power of 18 electrons. So 1 volt is for every 6.25 times 10 to the power of 18 electrons, you have used up 1 joule. What if you have like 9 volts? So for 1 coulomb, which is 6.25 times 10 to the power of 18 electrons, you have used up 9 joules. So 9 volts would be 9 lots of 1 joule per 1 coulomb. What about current? Now charge is the same, so 1 amp would be 1 coulomb per second. So that means for every second you have 6.25 times 10 to the power of 18 electrons passing through that point. So that would be 1 amp. Now what happens if you multiply them together? So you know that voltage is energy per charge and current is charge over time. You multiply them together. Can you see that charge is on the bottom of the voltage and charge is at the top of the current, and the charge cancels out, so you end up with energy per time. And that is the definition of power. So power is energy over time. Now that we know that if you multiply voltage and current together, you get power, we can put them together. So power is equal to current times the voltage. Let's bring in another equation using Ohm's law, V equals IR. So we know that power equals current times voltage, P equals IV. So P equals I times IR, where V equals IR using Ohm's law, substituting. P equals I squared R. So that is another formula for power. P equals IV becomes P equals I squared R. Alternatively, you can rearrange, change the subject to I, and you get I equals V over R. And so you have P equals V squared over R. So P equals I squared R, P equals V squared over R. Now, if we define power as energy over time, let's rearrange to get energy. So energy is equal to power times time, and we know that power equals current times voltage. So put them all together, we have energy is equal to power times time, and we know that power equals IV. So energy is equal to IV times time, and you get ITV. So energy, or work done, is equal to current times time times voltage. Let's have a look at this example. So example 1, you've got 12 watts is the power of a tablet charger. A phone charger is half of that. What is the current available by the tablet charger when the voltage is 5 volts? Let's label the quantities. So we have power equals 12 watts. You've got voltage as 5 volts. Using the equation P equals IV, rearrange for I, you get power divided by voltage. So you get 12 divided by 5, that gives you 2.4 amps. For example 2, you've got a kettle that has a heating element and it has a small resistance. If a current of 12 amps flows through the 20 ohm heating element, calculate the rate of energy transfer. Now the rate of energy transfer is power, because rate means divided by time, and energy transfer is moving from points A to B. So we need to use energy divided by time, which is power. And you've got the equations P equals V squared over R, or P equals I squared times R. Now in the question you've got A, which stands for amps, so it is for current, 12 amps, and you've got ohms, so you've got resistance. So you need to use the equation involving I and R, so P equals I squared times R. So P equals 12 times 12 times 20, that gives you 2,800 watts. Right, in order to do this question, so question 3, compare a resistor, a thermistor, and an LDR. Question 4, the graph in figure 6 is a logarithmic plot of the resistance of an LDR against light intensity. Use the graph to estimate the relative light intensity when the resistance is 1000 ohms and 50 kilo ohms. Now, if you look at the axis, you've got log. Now, LG stands for log to the base 10. So log to the base 10 brackets are in kilo ohms. So you need to convert whatever units you have in kilo ohms. So for A, it says 1000 ohms, which is 1 kilo ohms. So you do 1 kilo ohm over 1 kilo ohm. So in this case, it is 1. So when you put R as 1 kilo ohm, you do log to the base 10 of 1. Log to the base 10 of 1 is 0. So anything to the power of 0 is 1. So you look on the y-axis, 0. You go across. Where it hits the line, that should be about 1.4. 1.4. Now, because again on the x-axis it is log to the base 10. So you do 10 to the power of 1.4. This is for A. For B, 50 kilo ohms. So you do log of 50. So what is log of 50? On the calculator, you need to do log of 50. We know that the log of 10 is 1. Log of 10 to the base 10. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. So you know that is in between 1 and 2. So again, you look at the value between 1 and 2. Where it hits the line, you go down on the x-axis. Whatever that value is, you need to raise that to the power of 10. So let's just say, I don't know what that value is. So let's just say that it is 1.3. So 1.3 on the y-axis, you go across. Where it hits the line, you go down. So that is about minus 0 point something. So then for B, you need to do 10 to the power of minus 0 point something. Right, and then the summary questions here. So this is the summary questions for 9.10. So answer these questions at the back of chapter 9.10.